This video is about solving a particular homework problem from the WebAssign, and here it is in particular. The child slides down a slide with a 25-degree incline, and at the bottom her speed is precisely 1/4 what it would have been if the slide had been frictionless. Calculate the coefficient of kinetic friction, that's μk, between the slide and the child. So first, let's look at the frictionless case. Draw a picture of the incline or the slide, and a box to represent the child, and a free body diagram of the child, gravity, normal force, and the acceleration down the slide in the x direction is the sum of the forces in the x direction over the mass, which in this case is just the horizontal component of gravity. Not the horizontal component, I'm sorry, the x component, where our x direction will be along the incline and our y direction perpendicular. So if the angle that the slide makes with the horizontal is theta, then the angle that mg makes with our new y-axis is also theta. So if we look at the triangle with the components, here's mg, mg y-axis component, and mg x-axis component, and the x-axis component is opposite, so the x component of the force of gravity is mg times, since it's opposite, sine of theta. So we can put that back into our equation, mg sine theta over m. So the acceleration in the x direction is g sine theta. And then we can use kinematics to figure out her velocity if there were no friction. So the equation we want to use would be v final squared minus v initial squared is 2 times a times her displacement. The reason we choose this equation is that her displacement on the slide is going to be the same in both cases. Her initial velocity is 0, and her final velocity squared is 2 times g sine theta times however long the slide is. So that's 2 times 9.8 times sine of 25 times delta x. Taking out my calculator and plugging this in, I get 8.28 times whatever delta x is. And so v final is the square root of 8.28 times delta x. So now it says the speed at the bottom is 1/4 of what it would have been if it were frictionless. So the speed of at the bottom is 1/4 of the square root of 8.28 times delta x, or v final squared is equal to 1/16 of 8.28 delta x. So I divide 8.28 by 16, and I get that the v final squared is 0.518 times delta x. Therefore, I can find the acceleration in the case where there is friction. So I go back to this same equation that I have down here, and I say that v final squared minus v initial squared is 2a delta x, and v final squared is 0.518 delta x, minus 0 is 2 times a times delta x. And in this case, the delta x cancels, and dividing both sides by 2, I get that the acceleration is 0.259 meters per second squared. So now I go back and I draw a free body diagram of the child on the slide with friction. So gravity down, normal force up, friction opposite the motion. I add my coordinate system, and I write an equation for the x direction acceleration. AX is mg sine theta. That's the component of gravity down the incline, minus force friction over the mass equals the acceleration. So, and the force of friction is mu times the normal force, and the normal force is opposite the y component of gravity, which is adjacent to my angle, so that's going to be mg cosine theta. So the force of friction is mu mg cosine of theta. I can substitute that back in, and the acceleration in the x direction is mg sine theta minus mu mg cosine theta, all divided by the mass of the object. What I notice now is that both terms in the numerator have an m, so I can divide those out. In other words, cancel the m's, and I get that the acceleration is equal to g sine theta minus mu g cosine theta. So I'm going to scroll down to give myself a little bit more room. So 0.259 meters per second squared is g, 9.8 meters per second squared, sine of 25 minus mu times 9.8 meters per second squared cosine of 25, which means that mu, a little bit of algebra later, the coefficient is equal to 0.437.